Hello and welcome to another physics lesson. Today we'll be looking at Newton's law of gravity. So as the legend goes, Newton was sitting next to an apple tree and he saw an apple fell. Perhaps it hit him in the head. And from that he was able to discover gravity. Apparently Newton was the first person to figure out things fall. Now I know what you're thinking. You're thinking, Mr. Kramer, Mr. DeCrane, Mr. Elliott, whatever your name is, I forget because I haven't been at school for a while. I may not have a fancy degree from BS University like you, but I'm not an idiot. I know people knew things fell before Newton. 2-year-olds know things fall. And you'd be right. Everyone knows things fall. In fact, Galileo, about 200 years earlier, was the person who discovered that all objects fall at the same rate. So why doesn't he get credit for discovering gravity? Why does this bozo, who had already discovered 3 laws of motion, gets credited with inventing calculus, and discovered that his law of cooling and laws of optics, why does he also get credit for the law of gravity? Well, it turns out he actually did make a pretty remarkable discovery about gravity that previously wasn't known. You see, at the time, people knew things fell, and they called that gravity. But they also knew things moved in circles. Well, more accurately, they knew planetary bodies moved in circles. So we have the planets and the moon, and the Earth is going around a circle around the sun, and they called that planetary motion. And no one really knew what caused that either. And in fact, no one even recognized there was a connection between these two things. You could go back and look at some of Galileo's writings, and he actually describes them as 2 different phenomenons. He says in one of his writings, you give me the name gravity to explain why things fall, but you don't actually know what gravity is or what causes it. You know no more about gravity than you know about what causes the planets to move in circles. And that's not a direct quote, that's a paraphrase. The point being, he was describing it as if it was 2 different phenomenon with different causes, and saying that the person that he was arguing with didn't understand what caused either thing. So one thing that Newton discovered was that it actually was the same thing. And so let's look at how he did it. So Newton knew a few things. He knew that he knew his second law. He came up with it, and his third law. So he knew that net force equaled ma. He knew that for every action force, there is an equal and opposite reaction force. He knew that for objects in circular motion, that you could find the acceleration with v squared over r. He knew the radius of Earth. So you may have come across that before in a math class, that the radius of Earth was first estimated by a Greek mathematician about 150 BC by looking at the sun shining in a well. Yeah, I'm not going to say more about that now. He also knew the distance. My S disappeared for some reason. He knew the distance from Earth to the moon. Now this one surprises people because this one usually you probably have never come across this, but this was actually first estimated in 260 BC by another Greek mathematician by looking at how long it takes for a lunar eclipse to occur. And so if you're interested in that, I'll try to remember to post some links on Classroom explaining how these 2 things were actually discovered. Now he knew that the moon, since it's orbiting Earth, must have a force on it. It can't be that it just moves in a circle naturally. That based on his laws, he knew his first law, which I should have put up there I guess as well as a known thing, he knew from his first law that an object will move in a straight line unless there's a force acting on it. And so since it's moving in a circle, there must be a force. And that force would be given by this equation. Since it's a circular motion, we can use this equation here to figure out what it is. And he reasoned that gravity was that force, that it must be the same force that acts on this moon as acts on this apple. That was actually his revelation. that the moon is actually a falling object. It just happens to be falling around Earth. So, I said, well, let's think about what factors affect this. So if I had a 1 kilogram apple, it'd be acted on by a 9.8 Newton force. If I were to then take an object that was twice as massive, let's say a watermelon, anyway, a 2 kilogram watermelon, and let's say it then would have a force of gravity on it of 19.6 newtons. So we can see then that the force of gravity is proportional to the mass of the object we're talking about. So force of gravity is proportional to the mass of object 1. Now if we go to third law, we say, well, all forces are interactions between two objects. We have the Earth pulling down on the apple, but the reaction is the apple also pulls up on Earth. We have the watermelon, Earth pulls down on the watermelon. Well, the watermelon must pull up on Earth, and those forces must be equal and opposite. So 9.8 newtons down, well, that gives us 9.8 newtons up. And so he logically concluded then that if doubling this mass would double the force, well, shouldn't that be true for the Earth? It doesn't really matter which object we call the action or the reaction. So doubling the mass of the Earth must also double the force of gravity. So the force of gravity must also be proportional to mass 2 of whatever the second object in that interaction is. Now, reasoning that gravity must also be responsible for planetary motion or orbital motion, he looked at, well, how's the distance of the moon compared to the distance to these apples? So the apples would be about 1 Earth radius from the center of Earth. But the moon is about 60 times further away. It's 60 Earth radii distance away. And when we talk about them making these measurements in ancient times, a lot of times the measurements were actually done this way, not necessarily in a hard number like what we have now, but saying, oh, the distance must be 60 times the radius of Earth. Of course, since the radius of Earth was known, then Newton was able to get an actual number on that. Anyway, I digress. And so you plugging in the actual numbers, when we look at how long does an orbit take, what's the radius of that path, what's the circumference of that path, he had the information he needed then to get the acceleration of the moon. And he was able to figure out that the acceleration of the moon was 1/3600th of the acceleration of the apple near Earth's surface. Now this number might not be immediately obvious, the significance of it, but that is 60 squared. So if I square 60, I get 3600. And so that led him to conclude that the force of gravity must be proportional to 1 over the radial distance squared. Radial distance being the distance from the center of one object to the center of the other object. So we take these three relationships that he got. That gravity is proportional to the mass of object 1. It's proportional to the mass of object 2. It's inversely proportional to the radial distance squared. Again, the radial distance being from the center of mass 1 to the center of mass 2. These are the factors that affect gravity. And combine those all into one proportion, we get gravity is proportional to the product of m1 and m2 divided by the radial distance squared. But that cannot be the final equation. He knew he had a problem at this point because the units aren't right. This is a force. The units for a force are newtons. If we look at a newton is a kilogram times a meter over second squared. But this, if we use standard units, would be a kilogram times a kilogram, so it'd be kilograms squared on top, divided by meter squared on bottom. So kilogram squared divided by meter squared is not the same as this. So Newton had to do something that we might all do in his situation. He made up a variable and put it in front of his equation. He called it the gravitational constant. He said, I don't know what it is, but there's some other factor that must be affecting gravity. Now, this might seem really strange or a little bit like cheating, but really he's just acknowledging that he doesn't have the whole picture, that he's figured out quite a bit. He's figured out that gravity is the thing that makes the moon travel in a circle. He's figured out that it is affected by the mass of the moon, the mass of the earth, and the distance between them, and that that is true for all objects. But he hasn't figured out enough to actually explain everything that affects it. And in fact, at that time, the mass of Earth wasn't known, and you would need to know the mass of Earth to calculate g, and you'd need to know g to get the mass of Earth. And so he was kind of stuck. So this equation at the time was only really able to give kind of the relationship, talk about the factors that affected it, but we weren't able to actually calculate gravity. That came about 100 years later when g was finally measured. So g is a number that at this point we believe is a property of the universe. G should be the same everywhere in the universe, and it makes this equation kind of work out. We call it the gravitational constant. We call this equation the law of gravity. Now it's important to point out that it's called a law because it matches observation. There's nothing in here that explains why gravity acts the way it does, or what causes it, really, how it works, but we know how it behaves, and this matches observation, and so it's a useful equation to us because it is able to make useful predictions. So, in summation, what Newton discovered is that gravity is universal, that everything attracts everything, with a force that is proportional to the product of their masses divided by the radial distance squared. All right, so that pretty well does it. I went a little bit long, so I'm going to cut it off there. Thank you for watching.